This is Lecture 10A for Calculus 2 on changing parametric equations into Cartesian form. It's not always easy to algebraically change these parametric equations into the Cartesian form, which would be y as a function of x, is what I'm talking about with Cartesian form. It's not always easy, and sometimes it's not worth the trouble, because sometimes that Cartesian equation is so complicated that it gives you no insight into the problem at all, no insight into the graphing at all, and you're very content to leave it in its parametric form. On the other hand, there are some Cartesian equations that are very simple and provide you with much insight, and I'll give you 3 or 4 examples of those in this lecture. For the first example, let's use the equations, the parametric equations, from the first lecture, the first example in the first lecture. In this case, x, which is a function of t, the parameter t, is a cosine function, and y is b times the sine of the parameter t. Now, to change these into the Cartesian form, I'm going to use the Pythagorean theorem for trig functions, which is cosine squared plus sine squared equals 1. So if I look at these original equations, I can rewrite them in terms of cosine and sine, and that's done right here. And then if I substitute these into that Pythagorean equation, I get x squared over a squared plus y squared over b squared equals 1, which is the equation for an ellipse. And if a equals b, such as in the first example in the previous lecture, in which a and b were both equal to 10, then you get a circle. So this shows the relation between x and y, and this tells you, in this case, that you would either get an ellipse or a circle when you plot y versus x. Here's another set of parametric equations. Let's let x be secant t and y the tangent, and a and b are the amplitude of those functions. We're going to use the same Pythagorean theorem again, but written in the form of secants and tangents. Secant squared minus tangent squared equals 1. Do exactly the same trick as before. Using the original functions, we can write secant is x over a and tangent is y over b. When I substitute it into this form, I get the following equation, which is the equation for a hyperbola. So this is another one in which a Cartesian equation gives insight into the graph. That is not unique, though. Here's another parameterization of a hyperbola. Let x be some amplitude a times hyperbolic cosine, and y is b times hyperbolic sine. We do same as we do before. Here I'm isolating hyperbolic cosine and hyperbolic sine, and using this identity, cosh squared minus sinh squared equals 1. The result is, again, a hyperbola. Now I'm going to show you the parametric equation for a line, or one parameterization of a line, and this will also point out an important point about parametric equations. So let's start here with x as some constant a times sine squared, and y is b times cosine squared. Again, we're going to use the same Pythagorean identity. We'll get a lot of use out of it here, but let's write it as cosine squared equals 1 minus sine squared. And using these substitutions, all right, we'll have, let me get the pen, sine squared is x over a, cosine squared is y over b. When I substitute it and multiply through by b, I get this, which is just the equation for a line with slope minus b over a and a y-axis intercept of b. Right. Now, the important point here is this line does not extend to infinity. It came from these parametric equations. This Cartesian equation, y equals b minus b over a times x, is just a Cartesian form of the parametric equations. Right? If you were to graph this, you could only graph on their points of x and y pairs, coordinate pairs, that corresponded to the same time. But look at the first equation right here. What's going to happen with x? X is going to vary from 0 to a, because sine squared varies only between 0 and 1. Similarly, b varies between 0 and b. Right? those are the only values of x and b that get translated into the x and y plane. This line, although it is an equation for a line, does not extend to infinity. And unfortunately, we did not express the limits, but that's why we're talking about them here. So this is the point I'm trying to make. In the parametric equations, x and y trace out values repeatedly between 0 and a for x and 0 and b for y. When this gets translated in the Cartesian coordinate system, this line is traced out repeatedly, but it varies from its endpoint when t equals 0, x equals a and y equals 0, and then at 2 pi, well at pi, we have the other endpoint of this line, 0 and b. X is 0 and y is b. I'm thinking about this, and I'm thinking I did this wrong. Okay, I wrote them in the wrong order. At this point, t equals 0. All right. And here, t equals pi over 2. Trying to write with a mouse. Okay. But let me draw this a little bit of a graph here just to show you what I'm talking about. Okay, here's my coordinate system. And now this line is going to go from B, which would be right here, and let's assume A and B are positive. It's going to be this little piece of line here, and we'll let this be A, say it's positive, and B is positive up here. This is my y-axis. This is my x-axis. So when t is 0, x is 0, but y is b. So I'd start here, and then the line will move down, not in that fashion, but in a straight line down to this point. Then it will reverse itself. Let me get a straight line. It will reverse itself and go back up, and then it will reverse itself and go back down, and we'll do that repeatedly because it's reflecting what x and y are doing in terms of t. Let's look a little bit about going the other direction. Say you have a Cartesian equation and you want to write it in parametric form. Well, if it's not an equation that came from physics or economics or something where you have a reason for writing the parameterization, in which case the reason dictates the parametric equation. Here we're just saying I have an equation, let's let it be y equals x squared plus 6. Can I write that in parametric form? If you let x equal t, then you substitute t for all the x's. Now you have a parametric form of the equation. You could graph them separately, or then of course it would be a parabola in the Cartesian plane. And as I mentioned here, this is a very trivial example, but the procedure holds for more complicated equations. Right now you've written y as some function of x. Let x be t, all right, and then substitute t for all the instances of x in your original function, and now you have your set of parametric equations.